Hi there. Welcome for those who just joined us, and welcome back to Programmers Week for those of you who attended our Tech Talks and keynotes this week. Today we have the Data and AI Day, and my name is Alin, for those of you who joined late. I'm the Community Manager for Mobile and AI, and I'll be your host today for our AI Tech Talks. In our company, we have a culture of embracing knowledge sharing and also going outside the box or outside of your comfort zone and trying something new. And a group of senior QAs have actually decided to tackle an AI project by themselves. So for this, they have committed design, implementation, testing, and have a continuous community involvement for feedback for the past 6 months. So I will let them introduce themselves and present their experience and what they have worked on so far. So guys, the floor is yours.
Thanks, Alin. Hi, everyone. My name is Vasile, and I'm going to start the presentation we have put up for you today. The title is We Walked into AI as it's something new for us, and we wanted to find out what are the challenges to implement such project and what it takes to test an AI program. Here's the table of our contents for today. And before we move forward, let's meet the team. So we are a team of folks with QA backgrounds. Alex Colta, we have here is the technical lead that also had the idea to start this project and put the team together, talk to each of us to see what roles to take in the project and start working on it. Marius, Catalin, and Ioan are senior QA automation engineers that help contribute in the implementation and, of course, testing of the project. And I am a team lead, also business analyst, and I have the role of a project manager and also a QA for this AI project. Before we start getting into the nitty details of our project, I think it's a good idea to go through the history of AI. So most of you learned of AI as being something of a 20th century the culture trend. So I think that people should realize that the AI and particularly animated beings that resemble humankind were in human history many millennia before. So we have in ancient times, in the Jewish culture, for example, the notion of golems. In Greek mythology, of course, we have Talos, which is a big metal construct that was animated, and he's supposed to protect the island of Crete. I mean, the island of Europa, which is part of Crete. Also, closer to our time in alchemy in the 1600s. In the study of alchemy, there was this notion of animated clay-like structure that resembled somehow human, and it was called a homunculus. Then moving in the modern times, at the beginning of the 1900s, we started to see Hollywood blockbusters like Wizard of Oz and Frankenstein that you have here on screen. There was also some kind of fantasy depicted human-made structures. And starting off with the scientifically and research and development part of things for AI, the first noteworthy conference was held in 1956 at Dartmouth College by John McCarthy and Marvin Minsky. A lot of people living in the AI community call those guys like the forefathers of AI. And here it was discussed the first ideas of where AI can take humankind, what are the most important projects to start working on, and from here the trend of AI was pushed into politics. Also, this way AI research and development managed to get funded, and some project debuted about the mid 1900s. Another noteworthy thing that happened to AI was in 10 years after the conference in 1956, when Alan Turing tried to answer the simple question, can machine think? So he developed the Turing test. The Turing test can be seen here in the right of the screen. So A is representing as a image, as a machine, B a human, C another human. They are all divided by concrete walls, let's say, and they can exchange pieces of paper where one of the participants in the conversation ask the questions, then the one that has been asked the question gives back an answer. So, for example, in this three-way interaction, if C, for example, the person there marked C, cannot determine if the conversation is from a machine and cannot differentiate between A and B in their answers, then it's said from the Turing test perspective that A, an artificial intelligence machine, has passed the actual Turing test. Another noteworthy thing that happened is the development of Moore's law. So by the 1970s, Moore started to make a prediction based on the evolution of information systems, or more specifically of the performance of computers, of machines. So as you can see in this graph here, we have all the noteworthy processors that were developed since the 70s up into late 2010s. And as you can see, there is a linear progression to how the performance increased. So back in the 70s, Moore thought that, yeah, like in a couple of decades or so, we will certainly have the machine power so we can develop very complex AI systems. Being in the 2020s right now, we can say that it's partially correct what he predicted, because like in the last couple of decades, the processing power has kind of calmed down. But besides computing power, there also needs to be algorithms, and of course, which I think is more important, it's the data from which the AI programs can learn from and truly become artificial intelligence or advanced artificial intelligence. Remaining in the 1970s, there was like an AI winter going on, like a decade. So after 20 years or more, like 15, 17 years, since the 1956 conference, when all those ideas were put forth, after 20 years, all the governments that were invested in AI and in projects of AI saw that progress was minimal. There were little to no practical projects after 20 years. So much of the world started to move away from AI and stop investing in such projects. A noteworthy thing that happened was that in the middle of 1980s, the Japanese government initiated the 5th generation computer project, which was creating computers using massively parallel computing and logic programming, again to make a platform to support future AI projects. This hadn't any practical any practicability in AI, as there were no noteworthy projects coming on from Japan in the 90s and early 80s and early 90s. So up until the 90s, there were some noteworthy things that happened that I already talked about. But most of you know, for example, IBM's Deep Blue program, which defeated Garry Kasparov in chess. Also, recently in 2016, Google made an AI program that beat the world's champion at Go, and it was really noteworthy. And I think that's it for major things that happened throughout the history in humankind, in AI, and the research and development that happened in the last century. That's it for history, and now we're gonna go through the project overview, what our team has been working on. So we'll start with what is this project. So we have the resources and tools to call it a fully fledged agile project. Like we have meetings, like we have a Jira system, we have a test management system where we keep our tests. We work with Java. We have a DB for our project, etc. It's a project born of our passion. Of course, every one of us here are very passionate about technology, about doing extra things besides our regular project at work, and constantly being engaged and challenged, building new projects. And of course, we also did this for having fun together. Like we sometimes plan get-togethers when we talk about our project and other technologies, and it's pretty fun. So the scope of the project is to design, implement, and test, of course, a set of AI algorithms that are compatible with warehouse logistics, and our project is a warehouse. Think of it like a warehouse from a big e-commerce site like eBay or Amazon, and how the warehouse manned and unmanned handles the user orders. Also, besides our actual project, what comes into it is the research and development with artificial intelligence, like looking at other frameworks, looking at AI algorithms, and see what best fits our project, and of course implementing it. We also started this project to prove that we can handle AI, especially in our QA community that we are part of. Share the knowledge with all the communities in our company, and of course, make something that is desirable for other technology enthusiasm and involve people to take part of it. As you see later, that having community involvement to provide us with that data is also a key success and metric for the success of any AI project. And lastly, before I let my colleagues talk about the technical challenges that we encountered during this project, I'm going to talk about short project evolution, short project history. So in the first phase, that was like at the beginning of the year, we started with designing and planning a working deterministic warehouse. When we have like one carrier that carries out one order, one user order, and has a drop point, imagine somewhere close to the margin of the warehouse, and figure out the tools needed, at least for phase 2. Of course, the figuring out of tools and everything was needed was carried in phase 2 and even now in phase 3. In the second phase of the project, we implemented and tested the deterministic warehouse. We have constant feedback and progress reports from both within our team and some people outside of our teams. We also made some in-house presentation about what we are working on and got some nice ideas from those presentations as well. We started researching and planning for AI integration, meaning the algorithms that we should have gone into a warehouse, also make the program more complex, like defining warehouse complexity, having multiple carriers inside the warehouse, order complexity, like types of orders, type of products that a warehouse can handle, speed for carriers, and multi-threading. Of course, some of these complexity factors didn't make it, at least right now in phase 3, but we're planning to continue evolving our system. And right now in the third phase, we have a basic AI algorithm implementation in place and a better UI, which you will see further down this presentation. Here I'm just throwing out a new UI that we presented to the community like 3 months ago. And this was the deterministic warehouse we built in phase 2 of our project. Further down this presentation, Alex will have a slide where he compares what we have in phase 2 and what we have now. Okay, so that's it for the history and the introduction to our project. And I'm gonna let Marius talk about a bit our tech stack.
Hello. So talking about tech stack, we're going to start with the technologies, because in the middle, as you can see, we have the programming language. We choose Java because all of us have experience in this language. And also this is a perfect combination with TestNG, testing framework, and Maven for builds and dependencies. And for continuous integration, we choose Jenkins because we need the ability to run multiple times, schedule builds, and generate lots of data for our algorithms. And since we're generating a lot of data, we need to store it somewhere. So storage being important, we need to keep history, track every session execution. and we choose MySQL for a database. And with the help of storing everything in a database, we can achieve infinite data generation for the Mediator training in the limited space of the warehouse. If we move further on to pathfinding, this was one of the trivial part of this project because we needed to find some algorithms that can find the path from source to destination. And here we choose 3 candidates, Lee algorithm, Romeo and Juliet, and depth first. Out of these 3, after testing and experimenting, we choose Lee. The other 2 algorithms are deterministic, and we move to the optimal one. And let me give it just a little brief. Lee algorithm is a maze routing solution, which is based on breadth first search. And also it is easy to configure. For example, if you wanted to move only in a certain direction and search for the path. But how does Lee work? Let's just see. Well, Lee, it first creates an empty queue, and in queue the source cell having a destination 0 from source itself, and marks it as visited. It will continue to loop that queue until it's empty, dequeue the front node. The pop node is the destination. If the pop node is the destination, then return its distance. Otherwise, for each of our 4 adjacent cells, it will mark +1 the distance and mark them as visited. When all the queue nodes are processed, the destination is reached, then you have a path. If not, then it will return false. If you have reached that destination, then you will get the number of movements and each step. And further on, I will give the mic to Ciuri to present you the in-depth.
Thank you, Marius. Hi, everyone. So in order to understand our project, I have described in this diagram flows the 2 main actors of our application. This one is for the carrier, the actor that actually does all the loading, unloading of orders. And the other one is the actual order itself. So to go through this diagram, we have the father time, the timeline. This has 2 purposes. One, to create the carriers necessary to provide the loading and unloading, and also to keep track of a global timeline during the project run. So here we have 1 carrier, but Timeline can create many carriers, and the carriers need to be assigned to a particular order. This functionality is done by the order bidding functionality, in which many carriers provide a bid. In this case, the bid is the estimated path from the starting point to the shelf that has the carrier. The carrier with the lowest bid actually wins the auction and is assigned that particular order. Once the carrier is assigned the order, it moves to the order shelf in order to load with that particular order. It captures the order and moves to the drop point where it deploys the order. Once that particular task is complete, it circles back to the order bidding functionality to carry on with to bid for another available order. Moving on. The order life cycle. Here we load all the existing orders from Google Spreadsheet, and one by one they are fed into the bidding functionality where the carriers provide their bid, as I mentioned in the last slide. Once an order is assigned to a carrier, the carrier goes to the shelves to find the order, and it is deployed to the unloading point, to the drop point where the order is complete and completed, and it is eliminated from the order list. All the available orders will remain in the order list to be bidded upon by the carriers that complete the previous task. Moving on, we have several functionalities, several algorithms to help us with these two flows. The first one is the timeline functionality, which is carried out by the timeline object. This functionality basically splits the time to carry from start to finish in certain moments. All carriers do one action per moment. As you can see in the right side of the screen, where we have a snapshot of one particular moment, the carrier performs an action, either move or wait. We will discuss about wait a little bit later. After it moves, it verifies if the destination is reached. The destination might be the proximity of the shelf, or the drop point, or the start point. If the destination is reached, we recalculate the carrier status from load to unload, for example, from unload to load, or other statuses. If the carrier destination is not reached, it means we have to perform another action, but that will be in the next timeline moment. So what are the advantages of this functionality? It helps with the collision detection. Because at any given moment in time, we know exactly where the two carriers are, and we can determine if there will be a collision or not. The second advantage is that the project, and in particularly the carrier, can be viewed as a state transition machine, where the state is a particular status at one moment, and the transition is the action performed during that moment. We first started with multi-threading these carriers, but there were a lot of complex variables that needed to be taken into consideration. So we eliminated the multi-threading, at least for now, because it gave the carriers too much independence, and we couldn't calculate, for instance, collisions, or we couldn't quantify its resources. How much time does it take for it to perform a task? Also, one of the advantages of this timeline functionality is that we can easily quantify the time and resources required for a carrier to perform a task based on how many moments in time it required to perform that task. Like I said, one of the disadvantages is that carrier independence is reduced, at least for now. And the speed, this moment in time makes the speed obsolete. We used to have at least 200 milliseconds per space, but now we need to reference ourselves to a moment in time instead of milliseconds. But there are future plans to reduce the moment in time and calculate speed based on the number of moments it takes to move a space. Moving on. This is the bidding functionality. It is based on weighted round robin, where every time a carrier reaches the status of bid, it calculates an estimated bid for a particular order. That estimated bid represents the path, the distance to the order, to the shelf that has that order, and the distance from the order to the dropping point. The winner carrier with the lowest distance, with the lowest bid, wins that order, and that order is assigned to that particular carrier in order to perform the loading and unloading task. Moving on. The third algorithm is the collision detection. We have identified 6 scenarios, as you can see in this screenshot, of collisions between 2 carriers. The warning sign in the middle is the point of collision, and there are, based on the pathfinding functionality that is up, down, left, right, we have these 6 cases. The winner of such a collision is calculated based on the angle of collision, 180 or 90 degrees, and it is calculated based on previous runs, meaning optimized path, and that will provide some rewards for different carriers and different orders. Based on those, we calculate a winner. The winner is allowed to move into the collision point, while the loser has its status set on wait to wait for that particular, for the winner to proceed to with its path. Only after the winner moves on, the loser will be able to move on. In regards to the metrics required to calculate the winner and the loser, I will let Ionica discuss about this next.
Hi everyone, I'm Ioan Cimpean and I'll be talking about the mediator. As the name states, the mediator is the one responsible to resolve a conflict between 2 carriers that want to move on the same position. So it takes into account the carrier positions, their order, and the position of conflict, like you saw in the previous image. This mediator will keep a record of or a biased list of each order, and it will update it after each iteration. So we start with 50-50 chances of being assigned as being awarded as a winner or being chosen, and then as we progress through multiple iterations, considering the same warehouse and the same orders, we will give rewards or penalties depending on the local and global success. And moving on, we do have some calibration points that we can use to, let's say, better generate our data and tweak what we have. So one point would be the warehouse structure. We can have a warehouse that have the shelves conveniently placed and also the roadblocks, and just leave narrow paths between, so we have multiple collisions. Also, the starting points are important, and the drop points, like let's say one carrier path, when it goes to load a shelf, it can intersect another one that's unloading its cargo. I mentioned the global and local success. So these are some flags that we calculate after, let's say, all the orders are complete for a warehouse. The global success represents that all the orders of the warehouse were delivered in the expected time, and the local success is based on the order. So each order has this field, and we do have some formulas to compute them. But in short, a success for an order is equal to having one carrier delivering that order without any collisions and being alone in the warehouse. multiplied by a factor that's between 1.1 and 1.9, so we can vary it, like if it has encountered multiple carriers, it has to wait. So even if there's a lot of traffic, it can deliver in this expected time. So after an iteration is complete, this mediator visits the bias list, and it will update each order based on that flag. There's also a collision decision process, and in the end, it will award a winner. Now, moving on, I will let Vasile discuss a little bit about the QA strategy.
Thanks, Monica. So, thanks everyone for filling out the details about the technical part of our project and the implementation and the algorithms being used. Now I'm gonna talk briefly about the QA strategy we employed, particularly for AI. This, of course, can be applied for any AI project. One is improve execution time over multiple program runs. So in a warehouse specifically, of course, we need to have optimized order execution. These can be placed on top order complexity, multiple carriers, and the identification of optimal runs. So that can be the run that the machine will learn from it. So we will apply machine learning on the particular run that we find as the optimal one based on the preconditions, inputted data, etc. Environment complexity, this of course comes down to the points that I briefly mentioned before, like the warehouse. A warehouse can have multiple floors, for example, all types of shelves, obstacles, and whatnot. And I left in here the doomsday fail-safe. Of course, if a program like this will be implemented in an actual real warehouse, we have to take into account safety measures. For example, the carriers shouldn't run into a human personnel or shouldn't bump into shelves to damage goods, or the carriers shouldn't go outside of the warehouse for whatever reason. And fail-safe programs can need to be implemented into our execution. And this all I mentioned needs to be tested thoroughly. As for the QA strategy, the classical test plan, test cases and results as test items, we have put together a test plan where we have everything that we talked about, plus the resources, the tools, test timings, what type of testing we are using, etc. Excuse me. So for the QA strategy, right now we have written some test cases in our test management program that are run manually, or we also plan to run automation tests for particular data sets and preconditions. These are some of the test cases for UI, for DB, the carrier, the warehouse, etc. And some conclusion to our project. But please don't go away. We have a special program run that Alex will show you after this slide. So after we've been working for 6 to 8 months now on this project, we are proud to say that we have a working AI. We are continuing to improve timings based on various data sets and preconditions to a project run, add of course scenarios. We are also very happy that we moved from the second iteration where we had a deterministic program to a fully fledged AI with AI algos. And we can say that we have reached the level to test non-functional scenarios when we can gather data and optimize based on the data. This data, of course, can be from our own program runs or involve data from other folks in the community, and whoever wants to join in with various ideas. And now I'm going to let Alex walk you through an actual program run and the data we collected for a program run that we have today. Thanks.
Hey guys, can you hear me? Next, I think. Okay, so this is basically our old UI. It showcases a warehouse model. We have used a model to describe our legend, just the items that are available in the warehouse. So long story short, we have carriers, we have merchandise placed on shelves, the letters, we have obstacles, we have pathways, drop-in points, and of course, a lot of orders. What we try to do is to increase complexity gradually. So we started from just one carrier, a small warehouse, few shelves, few orders. We end up adding a little bit of concurrency. We increase to 2 carriers, maybe we'll go, of course, we'll go even further than that. Regarding the mechanism that we have chosen for our system, we started with Lee. We end up using a more complex system. Now we have delved into AI to solve conflicts when multiple carriers tend to bump into each other. For this part, right now we have a natural selection algorithm, as my colleague has stated so far. And the idea, of course, is the best, let's say, the winning choices from previous iterations get promoted. They have a better chance to be picked in the next iteration, and so on. So this is the current model. Hopefully, we'll be able to advance even more with a proper neural network that will do more correlations that we can handle and provide even better results. Okay, can you please go to the next slide? Okay, so, but for the current moment, what we have here, we have progress shown through multiple iterations. You can see in the right table, we have iteration X, X plus 5, X plus 10, X plus 20. We have 2 kinds of, let's say, success metrics. One would be how many units per timeline are required to handle entire order list for a warehouse. You can see that it goes from 230 to 32, and then it starts to drop off a little bit. So basically, this is the learning mechanism. And we also have the local success rate for each order. You can see it varies. We have some formulas that we are picking that take into consideration when marking an event as successful, a collision as being treated successfully. based on local success and the global success of the timeline. So this is the moment we are right now. There are plenty of challenges. We have a bright future. The most important thing that we have to take into consideration right now is how we're going to scale it, keep it steady. We have the potential of unlimited test data for our warehouses, do all the combinations we can do for orders. So we can have a bunch of training data. Basically, the sky is the limit. So yeah, that's all from my side right now. I think we're out of time, right?
Yeah, thanks, Alex. So right now is the time for questions. And after this meeting, after this presentation, you can leave us feedback. For leaving feedback, just scan this QR code, and you will be presented with the form, and it takes like 1 or 2 minutes to leave your feedback there.
Thank you guys. So here's a question. What would you recommend to a tech enthusiast if that person who's if that person wants to get involved wants to get involved into AI projects? Just some quick starting point recommendations.
I think I can tackle this one.
Yep.
So the first step, of course, is to be around discovery. AI space is so complex, but there are some small items that you can follow up. The best example that I have, it's a small, it's basically YouTube videos and stuff like that. I have a small example. One would be a video named "The Machine That Learns." That's the core concept explained in, let's say, really easy language to understand. It's made by Vsauce too. But just in general, start to discover the space, start from wiki, start from YouTube videos and so on. At least from my end, I did this like for years and years, and it made me really excited about this field. We are also having some courses available, courses on Udemy, on other platforms, Skillshare and so on. So this would be a good place to start, and also try to find communities that study this part. They will help you join. Yeah.
Yep, thanks, Alex. So we had a question also on the previous talk that Alex Basinga gave about ML in testing. So I will address these questions to you guys since you are here after his talk. So do you think ML could be applied to assist in testing efforts? Of course, the answer will be yes. And how?
Well, it depends. If you actually want to use it as support for QA-related tools, that's already started to happen. For instance, on automation, ML is used for creating test cases that can heal themselves. It's a prototype, but it's a working prototype. It can also be used, for instance, when issues are being found, to classify them under bug-related or other parts, let's say maybe a system error, a test case error, and so on. So there are already some tools. I can name few. Would be Mabel, Report UI. It's a mechanism that basically does this classification that I mentioned before. And yeah, there are some tools. I expect that in the next like 5 years or so, the market will be flooded with AI-based tools. But meanwhile, AI is still, it's already being used, but in a smaller degree, just to handle small aspects of existing tools. I expect in the future this will be to a greater extent.
Thank you. Yeah. These seem to be all the questions. So thank you guys. Cool project. I love the enthusiasm. And also the fact that you took a challenge in a different field, let's say. So I think this will this will help you. Thank you very much. Thank you for listening in. Thank you for joining. There are also, after this talk, we will have data talks, and also later for the, let's say, for the night night guys, we have machine learning tech talks from US. So you can tune in that also. Thank you. Have a nice day.
Thanks.
Thank you. Bye.